Okay, so we are now gradually transitioning towards numerical relations and numerical functions. Okay, how they emerge from the problems that we're trying to solve, whatever the nature of the problem is. And this one is the problem is fairly practical. So maximum optimization problem. That's what it is. There are a bunch of them. So that's one of the most basic ones. Especially you can guess the answer. So we can just confirm that the answer that we have guessed, we guessed it last time. We can reproduce that result. But we do it in a slow manner so that we don't really. There is nothing especially important about this particular problem. The important thing is to discover methods that we can apply later. Okay. Methods, concepts, and so on. So starting with the recognizing functions and relations and functions. So once again, we're trying to maximize the rectangle. Okay, so okay, here it is. So we started with a problem as written above. So we have 100 yards of fencing material. We want to build a rectangular enclosure that is the largest possible. And if we try to put it in more concrete terms, we want to find the sides of the rectangle so that the area, its area, is the largest. Okay, we still do not have any symbolism, symbolic terms or algebra that naturally come in next. So then we make one step in the direction. We realize that we need the two dimensions. So one dimension, the width, we call W, the depth we call D. Then we know what to do if we assume that we know them. And we go through trial and error, then we put them next by each other, and then multiply them, and then that's how we know the area. So the problem that we discovered last time was that it's easy to run into combined dimensions in such a way that they will be either too large or too low, and that is a problem that we're doing, even though we're doing our trial and error on a piece of paper. I'm sorry, I have to. Excuse me, I have to ask you to turn off your computers, please. And so that we are doing too much work as it is. Okay, so let me go over this slightly in more detail. So before we arrive to where we arrived at the end of last class. So we're talking about the widths and the depths. Okay, all possible combinations of widths and depth, and they are both now, we were thinking of them as sets. Both of them are sets of numbers. So we're just trying to make sense of the problem and using the ideas that we have been talking about. So to begin with, we realize that these are sets of numbers, and it is a bit tricky to think of them in any way that is too precise. So we start easy, and we'll just say, how about we'll take these sets to be, we set them in increment of, say, 10 yards. Okay, so like the accuracy of our computation initially will be 10 yards. So it means that if we look at the widths, they will be 1, 0. Well, kind of stupid choice, but let's take it anyway. 10, 20, and up to how much? How far? 100, because that's how much material we've got. The same for the depth. So once again, from 0 to 100, all possible depths. So the trouble is that's what we discovered last time, is that not all combinations of these two are reasonable. Okay, but hypothetically, early on, it is okay to have two sets. You can even call them X and Y, or the possible choices of the rectangle. So each width plus each depth together give you a particular rectangle. That particular rectangle will have an area, and so you have a bunch of possibilities. Out of that bunch of possibilities, you'll choose the largest one. But what we're going to do now, we remember how we have done this before, and that is we put them in the form of a table, one for the widths and one for the depths. So depth 0, 10, 20, 100, and same for the widths. Okay, so two sets, and all the combinations of these two are possible. And then so that creates a table, and you can actually go on, and it wouldn't really take you a lot of work in order to solve this problem. But as a matter of fact, let's do that just for analysis of what we could do, if not what we should do. What's going on here? Okay. Who's doing it again? Okay. So I'll create a table, the one I just described, but now I'm going to be using a spreadsheet so that we could really use the help of it. So, okay, so I'll have, in this column, I'll have the, which I chose to be the widths vertically, so W vertically, and then to the right, I'm going to have the depths. Okay, so the depths are 10, 0, 0, 10, 20, 20, 30, 40, 50, 60, 70, 70, 70, 80, and 90, and 100. Okay, and similarly now the widths are here, so it will be 0, 10, 20, 30, 40. What is happening here? Well, typing machine. Numlock 20. Okay, and so now, so this is my table. This is my data. The two possible choices. Let me make the table look slightly better, like this. Okay, and now I could put numbers here that would do what? I will be multiplying these, so the table, the body of the table will be the areas. Okay, so I'll be multiplying the each of the, so for each of the locations over here, I will be multiplying, say, 30 by 60, and this number should be end up here. So I could carry out that fairly quickly if you know how to use Excel. Okay, so I'll be multiplying. Let me see, R2C. Okay, so that is. Okay, so R2C means second row, same column. Okay, multiplied by RC2. Let me, unfortunately, I have to fix this. There are options that are different. Where's the formula? Okay, this is better. Okay, so so vertical is number and horizontal number. Both of the like in a table, it will have both both columns and rows are done by numbers. Okay, so that's how it works out. RC2 times same row, second column, and R2C. It is the second row, same column. Okay, so I multiply these two. I fill the rest of the table. Okay, and I have all the numbers right here. Okay, so computing, so it's how many? 11 times 11, 11 times 11. That's 11 by 11 table, and I have computed all possible areas for all possible rectangles, ignoring that restriction. Remember, a restriction that we're supposed to be using. But otherwise, certainly it's very obvious that I should be choosing. If I had that freedom, I would choose the biggest possible width, biggest possible depth. That is so at the very bottom right. Okay, that's not helpful though. So we're gonna now figure out what to do about the restriction. But otherwise, this is how data is found. We just have to extract the data that is relevant, and the relevant data is here. What we got to at the very end of last class, right here. The restriction is that the restriction is. The restriction is here that the twice the depth plus twice the width is supposed to be equal to 100 yards. In other words, for it is the perimeter, or depth plus width is equal to 50 if you want to really make your life easier. So, okay, so if we look at this table, so the depth plus the width should add up to 50. We'll look at our table, and let's see if there is any data that we could extract. What is the relevant data in all of this table? So once again, the width that is vertical on that vertical column on the right, and the row at the top, the depth, they should add up to 50. Okay, so can you suggest one that works?
Say the width is 20 and the depth is like 30. So
20, this one, right?
Yes.
Okay. It's doing it again. This one. Okay, so let me mark it maybe like this, like that. That is not. Okay. 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 So why? Because 30 plus 20 is 50, so that works out. So 600 is a legitimate choice. We could get 600 square yards enclosure if we choose these two. But there is more. Can you suggest more?
You do the opposite of that.
30 and 20. Okay, this one. Okay, one more. Okay, can you see more?
40 and 10.
40 and 10, this one. So you can see a pattern forming. Another one, 10 and 40. Okay, and in fact, I could choose 0 and 50. There is no cows there because it has no width. But the pattern is clearer, right? So in fact, not only these are these choices of width versus depth satisfy our restriction, but in fact, none other do, right? And outside of this, of these 6 cells, none of them are properly. They are either too long or too much material or too little. Okay, so either I to go up and to the left, those are not using all the material, and if I are below these 6 red cells, they require too much material. So this is in fact it, and we don't have anything else. And what does it suggest? The answer to our question?
The greatest amount of like area you can have would be 600.
Probably 600 at our best, because if you think about it, there might be more when you have 600 and 600. You know, maybe if we take 25, right, it might give us bigger. In fact, it does. The limitations of this data that we have collected does not allow us to make draw that conclusion. But it is a start, and then we realize that these cells form form a line, and what that line is in fact the graph of our relation. So on the x or rather xy plane, if we prefer, width and depth, what our relation that we have been talking about, this one or that one, if you prefer, this relation gives us a straight line. Okay, so the dependence of D on W and W and D create a line on what? On our in our chart. So I could actually do it like this. What was it? It was from. They're missing 30 and 40 and 50. I'll erase this. Okay, 40 and 50, and these are the values that are appropriate. So these are feasible or possible. Possible combinations of width versus depth are here, and the rest are not. We discard them. Okay, so let me do what we did last time, and that is instead of a table, so pretty much we're looking at crosses, putting crosses in a table. Let's turn it into, once again, into a graph. And in the form of a graph, we're going to have, that doesn't really matter which way. How about I just flip this axis? So I'll call this, did I call it x widths? No, I called that x. So still call it y. Let's call this x, and we put it in the form that we have done previously, and that is we want y to point up, and we want x to point to the right, like this. Okay, and then our numbers run between 0 and 50. Turns out we don't want to go beyond 50, so we can just as well change that. And so these are x's. This is x, but it's also the width. Okay, and the y-axis is refers to the depths. Okay, and then my line of feasible choices for them is this. Okay, so that certainly helps us to, and the suggestion I'm trying to make here, in addition to what we have been doing, is that it might be made of points as we have done it so far, just like in this table, it's made of locations, one location at a time, but maybe, and that is ultimately we're going to arrive to that, it will contain all the points, not only one point at a time and we jump from one to the next. Maybe, in fact, it will be the whole intro, just like a pen. It includes every single point between these two. Okay, so that's a possibility, and we'll get to that. But really what we were trying to do here, just in addition to visualization of the graph of the relation, which is W plus D, or D plus W is equal to 50. Okay, so that's what we have visualized here, but the area has not come into play yet, the area. Okay, so how do we get the area into this? So let me first restate the problem, and it will be fine. We are making the problem more algebraic rather than geometric. So we will be, once the data is there and the setup is there, we have the two sets, x and y, we have the relation, we have the area formula for the area, it's just the product. Now we can state the problem in an algebraic form. So find find the values of W and D. We still remember that this refers to width and depth, but really it's not going to be important, such that we want them to lie between 0 and 50. So these are like our sets. Okay, and so that the area, I'll call it A, which is W times D, is the largest. Subject to a restriction. And that is W plus D is equal to 50. Okay, so that is, we are going clearly beyond just the common sense, but rather using the ideas from what we have been talking about here. Putting in everything into the algebraic form. So we introduced variables, named them appropriately, so that we still could draw some clues about what to do next. And we're looking for the area, which is the product of the width and depth, and that is what it is to be maximized. And there is a restriction to this combination of width and depth. So once again, this is a relation, and this we are really could try to, and we did over here, we tried to extract the information from nothing but the setup. So we just took all the data we have, and we selected the data that is feasible, and then tried to maximize. And it turns out that in the middle we have the two possible largest values, with possibly there's some hiding more even higher values elsewhere. Okay. So the way to solve the problem in a more effective way than that would be to actually get rid of one of the variables, one of the dimensions. So the dimension is W and D, and these two variables are related to each other. But what if, and that's the main idea, is turn the relation into a function. And so that there will be fewer variables to begin with. Well, we have 3, that's just too many. Okay, so so how do we turn it into a function? So remember the difference between relation and a function. Relation is literally, the question is, are the two numbers that we have related or not? Okay, and the relation tells you they are or they are not. And as you can see, if they are marked yellow, they are related. If they are not marked yellow, they are not related. So that's the whole thing about the relation. We just verify that condition with that equation, but otherwise it is really a trial and error process. So you have two numbers, you try it, plug it in, it works. The answer is yes. You mark it. If not, you don't mark it, and then that's your relation. But you cannot really get far with that because the algebra we cannot utilize the algebra here to the extent that we're going to need it. A function is, on the other hand, it is when there is a dependence of one variable on the other. Okay, so for example, how say W depends on D. Okay, so how does W depend on D?
If W is 20, then D has to be 30.
That's right. That is the nature of the function, right? If you know D, you'll know W. That's a function, right? So for every single D, there will be only one W. Okay? So you can see it here, right? You can see it here. If you know W, you know D, and vice versa. But what we want to do here is we want to make it algebraic. So in other words, we can just express W in terms of D. So W is what? No. What I meant is what do we do to our? This is our relation. And I want to take that's the same relation and turn it into a function, so that it split directly. 50 minus D, right? 50 minus D. So it's the same relation, but now it just takes a different form that is direct. So relation becomes a function. It's not always possible, by the way, but in this particular case, we're lucky, and we can just express one in terms of the other, and then this will be also not only the graph of the relation, but it's also the graph of the function. W is equal to 50 minus D. So why do we want it? The idea is to get rid of W. Since W depends on D, we don't need both of them. If we have D, we have W too. So let's just get rid of it. Take it out of consideration. And how? Well, so get rid of W. How? So look at the problem in the box. And here all three variables are present. How do we get rid of W? Well, yeah? No. We want to use the function. So we take our function like this and bring it into our problem, and just where every time we see w, we just replace it with 50 minus d. The operation is known as substitution. Okay, so we don't have to worry about the relation; it is already taken care of. But this is where that substitution will really make a difference. Right, so then the area will depend on the depth only. The width will be there invisibly, indirectly, through that relation. So in other words, it's going to be A is equal to 50 minus D times D. Right. Now let me write it out. The substitution itself is this. So area is equal to W times D, and according to our function, this is the same. Okay, if it is the same, they can be interchanged. And so I choose to replace W with 50 minus D so that I don't have to worry about D anymore. The result is profound, a profound simplification of our problem. So let me try to restate the problem in light of this new development. So find what? Find the value of W and D. Well, there is no W anymore. So there is a find the value 1 of D such that I still have to have a restriction on the depth between 0 and 50. Okay, such that area is equal to the formula we just found, 50 minus D times D. The end. There is no restriction anymore. So that restriction, the relation between W and D, has been used in order to get rid of the extra variable, but then they sort of kind of cancel each other. So you have really simplified things. So not only there is no W, there is also no restriction. The restriction on D that remains is only its domain, and that is, it has to be between 0 and 50. Okay, so as you can see how we shortened the problem, and so it is certainly simpler. But the profound observation that we need to make now is look at this formula, and we identify this as what? It is a function, yes. So once again, functions are popping up everywhere all the time. And so area is expressed directly in terms of D. No matter what D you plug in, you'll have the area. So that's the distance. Knowing the depth, you will know the area. Okay. So so let's do that with the formula is right here. I could just as well create what you appreciate how simple it is than this. Okay, so here we have 121 entries in my big table, and if you want to make imagine that if we try to do more and we try to go 1 yard at a time, then there will be 101 columns and 101 rows in order to compute all in one, and we still have to figure out which values are available and which are not. But this time, once one variable is gone, things will be much simpler because this is how I'm going to do it. Okay, so I'll put here, how should I put it? We know how to compute it, so I'll put the depth here, and I'll put, how about I'll put the width, which is the 50 minus depth, in the next column. It is a little bit small. Okay, so there will be a column of depth and a column of width, and then we'll multiply them and we'll have the area. Okay, how about that? Like this. So area is equal to depth times the width. Okay, so that's the idea of the computation. Then in the third column, we'll see all numbers that we need, and it's going to be just a long row. Okay, so if I do one at a time, let me start one at a time. So starting from 10, from 0 actually, since that's how we chose it. And then I'll just write it is equal to, I will add 10 at a time once again. Oops, what happened? That's not right. Equal this plus 10. Okay. Okay, and so I'm running up to 50. Okay, so we don't need these. Okay, so now I'm computing the width. So these are the 6 available depths so far. And then now I will subtract 50. So it is equal to 50 minus that. Okay. So these are my widths. Okay, now I just multiply them. Okay, so this is equal to this times that. Okay, and these are my areas. So what we saw in that big table, now we have a tiny table with only 3 columns. Okay, but the data is the same. So 0, 400, 600, 600, 400, and 0. Okay, so on the face of it, it appears that indeed 600 is the largest possible value. So if we want to do better than that, what do we do? If we are wondering if there is a better number or better dimension somewhere, what do we do?
Make our table bigger and have every individual number between 0 and 50.
That's right. So I don't want to do the whole 50. So how about let's make it. Well, that's also that would be a smart way to do it. That once you identify where you expect the largest value to lie, then you can actually concentrate on the interval between 20 and 30 rather than the whole thing. But let's just ignore that shortcut for the time being. So I don't want to make it too large. So let's go with 2 at a time. So I will go 2 at a time on and on. So I still start at 0, but the next one I will add 2 rather than 10. So there will be way more numbers. Okay, so so 2, there will be we're not going to need more than 25 rows in order to hit 50. Well, almost. Okay, so we are going to 50, and then those numbers below it don't make sense. As you can see, the width becomes negative. That's what happens when you step out of the domain. The width becomes negative, the area becomes negative, so the numbers don't make sense anymore. So that's why, as you can see, I'm erasing this because it's outside the domain. The domain goes to up to 50. Okay, but other than that, this column over here is very revealing. You can certainly look in the middle, and you identify that in fact there are 2 624 numbers areas that correspond to 24 and 26 dimensions. 24 by 26 or 26 by 24, they produce both naturally the same area of 624 square yards. Okay, so you can stop here. You can continue doing this. You can now go next 1 yard at a time, then 2, and that will give you more and more data. And but we are more or less satisfied. Certainly, probably a farmer wouldn't be feeling too bad with choosing to build an enclosure with these dimensions. Thinking a little bit as we did last time about it, we realized that the square probably is the best choice, and that's how you can arrive to this conclusion. But instead, what I want to do, I want to visualize it naturally. It's a spreadsheet, and it has graphic capabilities, and we have all the data, so let's just plot it. So as I did over the week, I am now plotting. I'm going to plot a scatter plot of this data. So before I do it, what are we looking at? We're looking at pairs of values the domain is the input, area is the output. So that's the one column highlighted is the depth, and then how it depends on it. We produce the areas of those rectangles. Okay, so I'll just plot it. I go and do the scatter plot right here. Okay, so see how nicely it looks. It certainly follows the value. So as you can see, on the x-axis we have the depth running from 0 to 50. On the vertical axis, you can see how we're running up to Something beyond 600, so we know it is 624. It appears twice, right in the middle of two dots. And that suggests more than just numbers, suggests that we are on the right track, and somewhere in the middle are the best answers right there. You can imagine if we go 1 yard at a time, there will be more points, and what will those points start to do? They start to merge together and form a curve. If in any doubt, you can go and in fact there is an option of in Excel you could choose different. Well, you can do it like this and turn it into a curve, or curve with points, or curve without points, like this. So it's the same data, but Excel does the work for you, and it connects dots with a curve, and then you realize that there might be a bump somewhere right halfway between the two between two largest values, 624. There might be in between even a larger number. So since this is a little bit of cheating because we don't have this data. This is the only data that we have. We have only the dots. This is Excel does it for us. So it is only suggests to us what to do, but really this is the data. But we could do better than that. Once we have this idea, we start thinking about maybe we've seen this before. What is this? If you've seen this before, it is a parabola. Indeed, it is a parabola. How do we know it's a parabola? Right. Yeah. Well, I mean, it does look like a parabola, yes. But if we go back to actual formula, look at the formula, we can actually tell that it's a parabola. The formula for the area in terms of the depth. How do you know what kind of formula is that? So you can see it here. Okay, so area is equal to 50 minus d times d, or 50d minus d squared. What kind of formula is this? Yeah. Okay. So how about how about f of x is equal to 50x minus x squared, if it makes you recognize it easier. So what is it? It's a function that you may have seen before, a formula that you have seen before. What do we call it? No, what? It is quadratic. Indeed, this is a quadratic function, quadratic polynomial, whatever you call it. And what we know, or will determine about them in this class, is that quadratic functions graphs are parabolas. Okay, so they either look like this or like that, but they're all parabolas. Okay, so once you get the idea that it might be parabola, you look at the formula. Indeed, it is a parabola. And then once you have that, you can actually finish the job with this job, and finding the highest value, but from theory of parabolas. And if you might, do you remember anything about the shape of a parabola? If this is 0, this is 50. Okay, so what is so special about parabolas? What does this help? What? They're symmetrical, right? You can draw a straight line through it, and it will be identical. So if you flip it like this, you draw it on a piece of paper, you flip it like this, it will be the same parabola. So which means to the left of this line are the x's. The graph is the same as to the right of it, which means that, what does that mean?
The same values on each side.
Right. Okay. So, where exactly?
Either the highest point or the lowest.
Right. Yeah, but what is the value of d? This one. It's halfway, right? So because of the symmetry, if it is 0 here and 50 there, then halfway will be the highest value, right? So that's what we know about the parabolas. the symmetry over its axis, and that axis will give you the largest value of that function. So this is the largest. Largest. This is halfway. So then what is halfway? It is 50 plus 0 over 2 is equal to 25. Then you still want to find the number, so 25 is the depth, and then the width is also 25, right? Is equal to 50 minus 25, right? Our formula is right here. That's our formula. So it's also 25, and altogether the area is 25 times 25, 625, I believe. Is it? Yes. Okay, so we get an extra square yard in that map, in that way. Okay. Okay, so we could have gotten that data from, if we went 1 yard at a time, we would discover that at 25, it is the highest value right in the middle, and whenever we move to the left or to the right, doesn't matter how close it is, we will get lower numbers. Okay, but that is a very revealing example of how you can do either data purely, and you can just use Excel like that. You don't want to do it by hand, but if you do it with any kind of software, such as Excel especially, spreadsheets, you fine-tune this data, or how should make it finer and finer data, and zoom in on particular values that you're interested in, and find out almost with absolute accuracy of what is that the largest value is. As long as the theory, however, you cannot entirely avoid theory because even though the numbers appear to be to fit the pattern, this data is revealing this, the other one too. But how do you know that there is no bump here somewhere? Maybe there is a bump here somewhere so high that we just missed it. Okay, so that's why the theory of parabolas becomes so crucial. It is the highest point, yes. But since there are infinitely many of points, and we can only get, say, 50 or 20, then there will be always gaps. And how do we know there is right inside of that gap? Maybe there is a bump. Okay, and even though if it is just an enclosure, then it might no big deal. But you can imagine a typical problem of this kind would be, say, a stock portfolio. And then you have, rather than having 2 parameters, you might have 1,000 different stocks and bonds or whatever. And then there are restrictions, relations between them, such as maybe because of the taxes, maybe you have some kind of proportions about you want to have stocks versus bonds and so on. You have to combine them together and optimize in pretty much this manner. And then a little bump might be worth $1 billion, right? So, okay, so I'll see you next week then.